Hello, in this video we'll be learning how to make a priority queue, and that takes input a digraph. So recall that a digraph like this, at least for us, is derived from a bunch of tasks that need scheduled. And then you have interdependencies among the tasks. Like for example, task 2 has to be done before task 1 can start, and also task 3 has to be done before task 1 can start. That's where the arrows come from. Also recall that the subscripts represent the task numbers, while the numbers in parentheses represent the amount of time it takes for that task to complete. So for another example, task 4 takes 2 units of time. And then to run the list processing algorithm, which is kind of the final goal of this, we require a priority queue. And so these are two algorithms here, decreasing time and critical path, that design a priority queue for us. So the first one we'll take a look at is the decreasing time algorithm. This one's very easy to run. It just requires that we list tasks in decreasing order, or sometimes non-increasing because they could be equal. So we just look for the task that takes the longest, which is task 6, and that goes first. Therefore giving it highest priority. So the idea for this algorithm is tasks that take longer get higher priority, and that's just how it goes. So we're going to list them out. So task 6 takes the longest, that takes 10 units of time. Task 2 takes 7 units of time, so that's the next highest priority. And then we have two tasks that take 5 units of time. So we have to decide which one in this tiebreaker we include first. So we'll just go with the lower number and include task 1 first, and then 7 after that. So then we have a couple of tasks that take 4 units of time. So we have task 3, task 5, and then finally these two, 4 and 8, have the same amount of time. So task 4 first, and then finally 8. And once I list all the tasks out, this is now my priority queue. So this is my priority queue given by the decreasing time algorithm with this digraph as input. The next algorithm to design a priority queue is called the critical path algorithm. And first we have to recall what a critical path is. That's a path in the digraph with the largest weight. That means that you add the time units as you go. And the critical path that we find first is this one, which starts at 2, and then it goes 2 to 1 to 4 to 6 to 8. So our first critical path is 2 to 1 to 4 to 6 to 8. Those are tasks. Task 2, 1, 4, 6, 8. If you add as you go along, you have 7 plus 5 plus 2 plus 10 plus 2. And that's the longest amount of time that you'll be able to find in a path. And you do have to obey the arrows, so you have to follow their directions. You can't say go here then up. You wouldn't be allowed to do that. And since this is the critical path at this moment, I'll take the first entry, the first task, and that's going to be the first entry in my priority queue. And then I'll remove task 2 from consideration, take it out of the digraph. And then you repeat that thing over and over, that same process. You find a critical path, record the first one, the first task, as your next entry in the queue, and then erase it. And then find a critical path, record the first entry, erase it. You repeat this process over and over until all tasks have been placed into the priority queue. So our next critical path that we get is 3 to 1 to 4 to 6 to 8. Which means task 3 goes next. That's the second highest priority. And then 3 is removed from consideration. And then in the rest of the digraph I find a critical path, and that one is 1, 4, 6, 8. So task 1 is next, and 1 gets removed. And that means everything all the edges going out of line get removed. It's gone. Okay, the next one is 5, 4, 6, 8. So that's task 5 next. And it's gone. The next one is 4, 6, 8. You can see this 4, 6, 8, that's a really long path in terms of time, and so that's being factored into all these. So 4 goes next highest priority, and then 6, 8, that's our critical path, so task 6, and then 7, 8, so task 7 is next, and then task 8 is left all by itself, so it is in some sense the critical path by itself, and so that gets scheduled. So if you have isolated vertices in the graph that are left over, those count as like a path of length 0. And this is the whole priority queue, so this is our output from the critical path algorithm. There were a few that I didn't erase along the way. That's just because we were just writing it out quickly, but in the end everything should be erased from the digraph. So those two algorithms, again, take a digraph as input and output a priority queue. They don't actually output the schedule. You would then use these priority queues, whichever one you chose, to then input into the list processing algorithm, and that would give you a schedule.